What if everything in the universe, every star, every galaxy, even the way time itself flows, follows a hidden blueprint we're only just beginning to decode? Think about that for a moment. The cosmos doesn't operate at random. There's an eerie order beneath the chaos, patterns so profound they hint at something far bigger than we've ever imagined. From the spiraling arms of galaxies mirroring the swirl of hurricanes on Earth to the way atoms arrange themselves in uncannily similar shapes across vast distances, the universe seems to whisper secrets in a language of repeating designs. And here's the wildest part: science is finally starting to listen. This isn't just about spotting shapes in the clouds of space. These patterns could be the keys to unlocking the deepest mysteries of existence: why the universe expands the way it does, how matter and energy intertwine, even whether there are realms beyond our own, echoing the same cosmic rhythms. Some researchers believe these hidden designs might point to a grand uniting theory, a single framework that ties everything together. Others think they could be evidence of something even more startling, that our universe is just one thread in an unimaginably vast tapestry. So today, we're diving into 30 of the most mind-bending theories about these cosmic patterns. Some will sound like science fiction, some might challenge everything you thought you knew. But all of them will make you look up at the night sky and wonder, what if we're standing on the edge of a revelation so colossal it rewrites reality itself? Buckle up, because this journey isn't just about observing the universe, it's about glimpsing the hidden code that might just explain it all. Take a sunflower, a seashell, even the way branches grow on a tree. What do they all have in common? They follow a sequence of numbers discovered by a 13th century mathematician, Leonardo Fibonacci. But here's where it gets cosmic. That same pattern doesn't just shape life on Earth. It's etched into the fabric of the universe itself. Galaxies like the Milky Way don't just spiral randomly. Their winding arms unfurl at ratios eerily close to the Fibonacci sequence: 1, 1, 2, 3, 5, 8, and so on, where each number is the sum of the two before it. Even the way galaxies cluster across vast distances mirrors this pattern, as if space itself is counting in Fibonacci's numbers. Planetary orbits, some researchers argue they dance to the same mathematical rhythm, with the spacing between planets reflecting these ratios. Why does this matter? Because if the universe leans on this pattern from the tiniest planet to the largest galaxy, it suggests something profound. A universal rulebook, a hidden code that underpins everything. Some physicists speculate this isn't coincidence, it's evidence of a deeper, possibly even intentional structure. Could the Fibonacci sequence be a fingerprint of the universe's design? Then there's the eerie part: quantum fluctuations, the tiny jitters in empty space that give birth to particles, might also follow Fibonacci-like patterns. If true, it means this sequence isn't just shaping the cosmos we see. It's woven into the invisible scaffolding of reality itself. That raises a wild question. Is math the true language of the universe, and are we just beginning to translate it? But what if the universe isn't just whispering through patterns we can see? What if it left deliberate messages in the very fabric of space? That's the startling idea behind anomalies in the cosmic microwave background, the afterglow of the Big Bang that permeates every corner of the cosmos. This faint radiation is like a snapshot of the infant universe, and most of it follows the smooth, predictable patterns scientists expect. But then there are the outliers, the strange, unexplained fluctuations that defy conventional physics. Some researchers argue these irregularities aren't random glitches. They could be imprints from something beyond our three-dimensional reality, like wrinkles left by higher dimensions brushing against our universe. Others take it even further. What if these anomalies are deliberate signatures etched into the cosmos by an intelligence so advanced it could manipulate the universe's birth itself? It sounds like science fiction, but the math doesn't rule it out. The most famous of these oddities, the axis of evil, a mysterious alignment of temperature fluctuations that shouldn't exist points in a single direction like a cosmic arrow, as if something or someone left a directional marker in the sky. And here's where it gets truly bizarre. If an ancient civilization had the power to tweak the universe's settings, altering the CMB would be the ultimate time capsule, a message that outlasts stars, galaxies, even entropy itself. Imagine finding a line of code hidden in the foundation of reality, one that only makes sense if you know where to look. That's the scale of what some physicists are seriously considering. Could the universe's oldest light be its most profound cipher? The answer might rewrite not just our understanding of physics, but of our place in existence. The golden ratio, 1.618, might seem like an abstract number, but its fingerprints are everywhere. From the Parthenon's architecture to the curve of a nautilus shell, this mathematical constant appears in nature's most stunning designs. Yet its influence doesn't stop on Earth. Look deep into space and you'll find spiral galaxies like the Whirlpool Galaxy or Messier 74 unwinding their arms with near-perfect adherence to the golden ratio. Their logarithmic spirals coil tighter or wider at precisely this proportion, as if some unseen hand sketched them using the same compass. But why would galaxies care about a number humans once used to design cathedrals? The answer might lie in efficiency. The golden ratio creates a spiral that packs the most structure into the least space without overlapping, a cosmic blueprint for stability. Star clusters and even the swirling maelstroms around supermassive black holes echo this pattern, suggesting it's not just about beauty but function. When matter spirals into a black hole, it doesn't chaotically collapse. It follows elegant, golden ratio-infused paths, minimizing turbulence and maximizing energy flow. Some theorists take it further. If the golden ratio governs structures across scales from hurricanes to galaxies, could it be a fundamental constraint of physics? A rule woven into gravity itself. Others propose an even wilder idea, that this ratio is a relic of higher dimensional geometry, a shadow cast by the true shape of the universe. After all, mathematics often reveals truths long before we grasp their implications. The golden ratio might be more than a curious pattern. It could be a silent architect, shaping the cosmos one spiral at a time. Imagine zooming into a tiny piece of the universe, a single atom. The flutter of a quantum field, then pulling back farther and farther until entire galaxies shrink to specks. At every scale, you'd start noticing something uncanny, the same shapes, the same rhythms playing out again and again. That's the heart of the fractal universe hypothesis, a theory so radical it suggests reality isn't just organized, it's endlessly repeating. Fractals are mathematical patterns that repeat themselves at smaller and smaller scales, like a coastline that looks jagged whether you're viewing it from space or through a microscope. In nature, we see them everywhere in fern leaves, river networks, even the branching of our own lungs. But what if the cosmos itself is the ultimate fractal? Picture galaxy clusters arranged in filaments and voids, a cosmic web that mirrors the neural networks in our brains. Zoom in, and you'll find galaxies with spiraling arms made of stars, which themselves might host planetary systems with miniature versions of the same spiral dance. Even deeper, quantum foam, the seething turbulence of space-time at the tiniest scales, ripples with fluctuations that eerily resemble the distribution of matter across the universe. This isn't just poetic symmetry. Some physicists argue it's evidence of a fundamental law, that the universe operates like a mathematical fractal with no true bottom or top level. That would mean reality isn't just vast, it's potentially infinite, with every piece containing a smaller copy of the whole. Ancient Hindu cosmology spoke of a universe where atoms contain worlds and worlds contain atoms. Today, cutting-edge simulations show matter clustering in ways that mirror fractal math, as if the cosmos is running the same algorithm at every level. But here's the twist. If the universe is truly fractal, it challenges our deepest assumptions about space, time, and even the Big Bang. A fractal cosmos might not have a single origin point. It could be a cascade of beginnings, endless and cyclical. That raises a haunting question. Are we stuck in a loop, watching the same cosmic story repeat forever? Or is this repeating pattern the signature of something even stranger, a universe that's not just expanding but constantly rewriting its own rules? Now, let's talk about a piece of math so strange, so elegant. It might be the hidden scaffolding of reality itself, the octonions. Most of us are familiar with the numbers we use every day, maybe even complex numbers with their imaginary parts. But octonions, these are numbers that exist in 8 dimensions, bending the rules of arithmetic in ways that make even mathematicians pause. Yet here's the wild thing. This obscure branch of mathematics could be the key to unifying the cosmic and the quantum, threading together the fabric of space-time itself. String theory, the leading candidate for a theory of everything, suggests that the universe's fundamental building blocks aren't particles but tiny, vibrating strings. But to make the math work, these strings need to dance in 10 dimensions, 6 of which are curled up so small we can't perceive them. That's where octonions come in. Their unique symmetry, a kind of mathematical perfection, might describe how those extra dimensions fold and twist, shaping the forces that govern everything from gravity to electromagnetism. Think of octonions as the universe's secret language. While regular numbers commute, meaning 3 times 4 is the same as 4 times 3, octonions break that rule. Their non-commutative nature mirrors the bizarre behavior of quantum particles, where order matters. Flip 2 electrons and you might get a different outcome than if you'd done it the other way around. Octonions capture that same unpredictability, hinting at a deep connection between abstract math and the quantum world. Even more compelling, the symmetries of octonions align eerily well with the standard model of particle physics, the framework that describes all known forces except gravity. Some physicists believe octonions could be the missing link, the mathematical glue that finally ties quantum mechanics to Einstein's general relativity. Imagine a single equation written in octonion math that explains why stars shine, why atoms bond, even why the universe expands at all. But octonions aren't just about particles. They might also dictate the large-scale structure of the cosmos, the distribution of galaxies, the way dark matter clumps, even the universe's accelerating expansion. All could be shadows of octonionic geometry playing out on a cosmic scale. It's as if the universe started with a set of 8-dimensional blueprints, then collapsed them into the 4-dimensional reality we experience, leaving behind echoes of its true nature. Of course, not everyone's convinced. Critics argue octonion math is too abstract, too divorced from observable physics to be anything but a beautiful curiosity. Yet history's shown us before mathematics often discovers reality's rules long before experiments catch up. The question isn't just whether octonions describe the universe. It's whether we're bold enough to follow the numbers wherever they lead, even into dimensions we can't yet see. Galaxies aren't just drifting apart as the universe expands. Some of them are moving in ways that defy all logic. Take hundreds of galaxy clusters scattered across billions of light years, and you'd expect their motion to be random, a chaotic dance dictated by local gravity. But in the early 2000s, astronomers noticed something unsettling. These clusters were streaming in the same direction, as if tugged by an invisible hand. They called it dark flow, and it's one of cosmology's most tantalizing enigmas. The numbers don't add up. The gravitational pull of all known matter in the observable universe can't explain this coordinated motion. It's like sitting in a boat, feeling a current drag you toward a horizon where no river should exist. So what's pulling these galaxies? One radical possibility is that the flow isn't coming from within our universe at all, but from beyond it. Imagine neighboring universes floating in a vast multiverse, each with its own distinct physics. If one of them happened to brush against ours, its gravity could imprint this strange, directional tug on our galaxy clusters. Critics argue it could just be a measurement error, a cosmic illusion, but the data holds up. Dark flow persists even in regions where the local distribution of matter shouldn't create such a coherent pull. Some models suggest these flows align with the same mysterious axis of evil we see in the cosmic microwave background, as if the universe is subtly tilted toward something unseen. Here's where it gets wild. If dark flow is real, it wouldn't just hint at other universes, it could reveal their structure. The direction and speed of the flow might encode information about the multiverse's geometry, like feeling the shape of an invisible object by tracing the ripples it leaves in water. We could be staring at the first tangible evidence that our cosmos isn't alone, but part of an endless expanse of realities, each with its own rules, its own stories. And yet, the most haunting question remains, what if these flows aren't random? What if they're signposts pointing toward something deliberate, a meeting place of universes, or even, dare we say, a cosmic highway? The answers might lie just beyond the edge of everything we can see. What if everything you know, every memory, every sensation, even the stars above her, isn't real but just a fleeting glitch in the chaos of the cosmos? That's the spine-chilling premise of the Boltzmann brain paradox, a thought experiment so unsettling it makes solipsism seem almost comforting. Named after 19th-century physicist Ludwig Boltzmann, who wrestled with the nature of randomness and order, this theory flips our understanding of existence on its head. Here's the core dilemma. In an infinite universe governed by entropy, where particles jostle endlessly, the laws of probability suggest something bizarre. Given enough time, random quantum fluctuations could spontaneously assemble a fully self-aware mind, complete with false memories of a past that never happened, far more easily than constructing an entire 13.8 billion-year-old universe. Think of it like shaking a box of Scrabble tiles for eternity. Eventually, they'll spell out a perfect sonnet, not because of design but sheer chance. A Boltzmann brain is that sonnet, a consciousness that pops into being, convinced it's lived a full life in a vast cosmos, only to dissolve back into the void moments later. The math is what makes it so haunting. Statistically, isolated brains arising from quantum noise are exponentially more probable than the orderly universe we perceive. After all, crafting one self-aware moment requires infinitely less energy and complexity than birthing galaxies, planets, and billions of years of consistent physics. So why do we find ourselves in a seemingly stable reality instead of flickering in and out of existence as ephemeral aberrations? Some physicists argue this paradox undermines our very assumptions about cosmology. If the universe is truly eternal or cyclic, Boltzmann brains should outnumber real observers like us by an unimaginable margin. The fact that we don't experience this, that our world feels continuous and coherent, might be the strongest hint that something's missing from our models. Possible solutions. One camp suggests the universe has a built-in expiration date, a cutoff point that prevents infinite time for these random fluctuations to dominate. Others propose we're fundamentally misunderstanding probability, or that consciousness can't arise from pure chaos without some deeper organizing principle. Then there's the wildest idea that we are Boltzmann brains and every moment we remember before this one is an elaborate illusion. But here's the flaw in that nightmare. If you're capable of questioning your own reality, you're already engaging in sustained thought, something a randomly generated brain wouldn't have time to do before dissolving. The paradox forces us to confront the fragile nature of observation itself. Maybe the universe isn't just stranger than we imagine, it's stranger than we can imagine. Or perhaps, as some theorists suggest, Boltzmann brains aren't a bug but a feature. If consciousness is the universe's way of observing itself, could these phantom minds be part of the process, flickering in and out like cosmic fireflies? Either way, the paradox leaves us with a humbling truth. In the grand casino of existence, we might be the most improbable winners of all. The world around us feels solid, tangible. You can touch objects, feel their weight, move through space in 3 dimensions. But what if all of this is just an elaborate illusion, a cosmic magic trick where depth and volume are nothing more than shadows cast from a flat, 2-dimensional surface? This is the heart of the holographic principle, a theory so counterintuitive it challenges the very nature of reality itself. The idea didn't come from science fiction, but from the study of black holes, those cosmic monsters where gravity is so intense not even light can escape. When matter falls into a black hole, it's gone forever, or so we thought. In the 1970s, physicist Jacob Bekenstein made a startling discovery. The information about that matter, like a cosmic receipt, doesn't vanish. Instead, it gets imprinted on the black hole's event horizon, the point of no return like data encoded on a flat disk. Later, Leonard Susskind and Gerard T. Hooft took this further, proposing that the entire universe might operate the same way. Our 3-dimensional reality, with all its galaxies, stars, and human experience, could be a holographic projection from a 2-dimensional boundary at the edge of space-time. Think of it like watching a movie. The screen is flat, but the images appear to have depth, movement, even emotion. The holographic principle suggests reality works similarly, with the true source code of existence written on a distant 2-dimensional surface we can't perceive. Quantum entanglement adds fuel to this fire. When 2 particles become entangled, they share information instantly, no matter how far apart they are, as if space doesn't exist for them. Some physicists argue this is because their connection isn't happening in our 3-dimensional world, but at that deeper 2-dimensional level where distance is irrelevant. Here's where it gets even stranger. If the holographic principle is true, it could explain why the universe seems to have a maximum amount of information it can contain, just like a hard drive has limited storage. The 2-dimensional boundary encoding our reality would have a finite number of pixels, meaning there's only so much detail any given volume of space can hold. That's why you can't zoom in forever. Eventually, you'd hit the resolution limit of the universe itself. Yet the most mind-bending implication isn't about storage, it's about identity. If we're just projections, do we really exist, or are we merely patterns flickering on some vast cosmic screen? The answer might lie in the math. Equations describing the holographic principle show that the information needed to describe a volume of space doesn't scale with its size but with its surface area. It's as if the universe is telling us the real action happens at the edges, not the center. Critics argue this is all speculative, a mathematical curiosity without experimental proof. But in 2010, a German team using gravitational wave detectors found unexpected noise in their data fluctuations that matched predictions of holographic universe models. Other experiments, like studying the cosmic microwave background for signs of pixelation, are underway. If they find evidence, it wouldn't just rewrite physics textbooks, it would redefine what it means to exist. After all, if reality is a hologram, then the greatest magic trick isn't in the stars, it's in the mirror. What if the universe isn't just governed by laws of physics, but by lines of code? The simulation argument isn't just a sci-fi trope. It's a serious hypothesis with roots in philosophy, physics, and computer science. The core idea is startlingly simple. If a civilization could one day create simulations so advanced they're indistinguishable from reality, the odds suggest we're more likely to be inside one than in the original universe. Think about the evidence stacking up. Space-time itself might be pixelated, with a fundamental limit to how small distances can be divided, just like the pixels on a screen. Quantum mechanics already shows us that energy isn't continuous but comes in discrete packets, as if the universe is running on a computational budget. Even the speed of light could be a built-in processing limit, preventing the simulation from overloading. Then there are the glitches, particles that tunnel through barriers they shouldn't be able to cross. Quantum entanglement, where particles communicate faster than light, behavior that defies classical physics but makes perfect sense if reality is rendering data on demand, skipping steps to save processing power. Some physicists point to tiny anomalies in high-energy particle collisions, moments when the laws of physics seem to stutter, like a game struggling to render an unexpected event. But here's the twist: the simulation argument isn't just about whether we're in a fake universe. It forces us to ask what a real even means. If a simulation is flawless, with pain, joy, and consciousness perfectly replicated, does it matter if it's artificial? Ancient philosophers pondered whether we might be shadows on a cave wall. Today, we're asking if we're shadows in a cosmic server farm. Critics argue there's no way to test the hypothesis after all. A perfect simulation would erase its own traces. Yet some scientists are trying. One team proposed hunting for jitter in ultra-high-energy cosmic rays, which might reveal spacetime's underlying resolution. Others suggest looking for mathematical patterns in physical constants, like finding repeating digits in pi, a signature of programmed reality. Whether the simulation argument holds up or not, it reshapes how we see existence. If the universe is code, then physics is its source, and we might just be characters in the grandest story ever written. The question isn't just, are we real? It's what happens when we find out. What if consciousness isn't just a byproduct of the universe, but the very reason it exists? This radical idea sits at the heart of quantum consciousness theories, where the line between observer and reality blurs into something far stranger. It starts with a simple but profound question. Why does quantum mechanics insist that particles exist in fuzzy superpositions, multiple states at once until the moment they're measured? The act of observation itself seems to collapse these possibilities into a single outcome, as if reality waits backstage until consciousness pulls it into the spotlight. One of the earliest minds to wrestle with this was mathematician John von Neumann. In the 1930s, he proposed that the collapse of quantum states couldn't be explained by physical processes alone. It required something beyond the material world, the observer's mind. Think of Schrödinger's famous cat, both alive and dead until someone opens the box. Von Neumann took it further, suggesting the box isn't truly opened until the information reaches a conscious being. In other words, reality might not fully exist without someone or something to perceive it. Decades later, physicist Roger Penrose and anesthesiologist Stuart Hameroff offered an even wilder twist. Their orchestrated objective reduction theory, ORCH or for short, proposes that consciousness arises from quantum vibrations inside tiny structures in brain cells called microtubules. These vibrations would dance in quantum superposition, processing information in ways classical physics can't explain, until they collapse into definite states, creating moments of awareness. If correct, it means your thoughts might literally be quantum computations woven into the fabric of reality itself. The implications are staggering. If consciousness plays an active role in shaping the universe, it could explain why the cosmos seems so finely tuned for life. Some interpretations go as far as to suggest that without observers, reality remains a fog of possibilities, a quantum soup waiting to be cooked into existence. Critics argue this veers into philosophy, not science, but recent experiments add fuel to the fire. Studies show quantum systems can behave differently when observed, as if particles know they're being watched. Even more bizarrely, delayed choice experiments reveal that measurements made in the present can retroactively influence quantum events in the past, bending causality like a cosmic feedback loop. Here's where it gets truly mind-bending. If consciousness and quantum physics are entangled, it might mean the universe is fundamentally participatory. We're not passive spectators but co-creators, our observations stitching reality into being moment by moment. Ancient mystics spoke of the world as illusion, modern quantum theory whispers they might have been onto something. The question isn't just whether consciousness shapes reality, it's whether reality can exist without it at all. Time seems to flow in one direction forward, dragging everything from stars to coffee cups toward decay and disorder. But what if time itself could crystallize, locking into repeating patterns that never wind down? That's the mind-bending promise of time crystals, structures so bizarre they defy the universe's most ironclad law, entropy. Unlike ordinary crystals, which arrange atoms in repeating spatial patterns like a diamond's lattice, time crystals repeat in time, cycling through states indefinitely without energy input. They're not just perpetual motion machines, they're perpetual motion baked into the fabric of reality. The discovery of time crystals in 2016 sent shockwaves through physics. Nobel laureate Frank Wilczek first theorized them in 2012, suggesting certain quantum systems could break time symmetry, the idea that physical laws work the same whether time runs forward or backward. Normally, shaking a system like jiggling a box of loose springs should randomize its behavior, but time crystals flip this expectation. When pulsed with energy, they settle into a rhythmic dance, ticking like a quantum metronome that never winds down. Imagine pushing a child on a swing, only to find they keep swinging between your pushes, perfectly spaced forever. That's the eerie precision of a time crystal. Now stretch this idea to cosmic scales. If time crystals exist in laboratories, could space-time itself harbor similar structures? Some cosmologists speculate the universe might be threaded with hidden temporal order, cycles nested within cycles like a Russian doll of repeating moments. This wouldn't just challenge entropy, it could rewrite it. Instead of a one-way slide toward heat death, the cosmos might pulse eternally, its arrow of time bending into a loop. Ancient Hindu texts spoke of cosmic cycles lasting trillions of years. Modern physics might be catching up. Even wilder is the implication for black holes. Near a singularity, gravity warps time so severely that some models predict it could fracture into crystalline phases, where cause and effect stutter like a skipping record. If true, falling into a black hole might not mean oblivion, just an endless, rhythmic reordering of moments, a fate stranger than any sci-fi. Critics argue time crystals are lab curiosities, not cosmic blueprints. Yet their mere existence proves that entropy isn't always king. In a universe where time can crystallize, the future might not be a fading ember, but an infinite kaleidoscope turning forever in the dark. The Big Bang, our universe's violent, fiery birth, might not have been a singular explosion at all. What if it was the cosmic equivalent of a white hole, the theoretical twin of a black hole where nothing enters but everything erupts? While black holes devour matter with relentless gravity, white holes would do the opposite, spewing out energy and matter in an irreversible cosmic geyser. And if our universe burst forth from one, the echoes of that event might still be visible today. The math is compelling. General relativity predicts white holes as valid solutions to Einstein's equations, just as real as black holes if far more elusive. Unlike black holes which form from collapsing stars, white holes can't be born from ordinary astrophysics. They'd need to exist from the beginning, as if the universe itself were a white hole's aftermath. And here's where it gets fascinating. Gamma-ray bursts, some of the most energetic events in the cosmos, fit the profile. These violent flashes, lasting milliseconds to minutes, release more energy than the sun will in its entire lifetime. Some exhibit spectral signatures that don't quite match supernova or neutron star collisions. Could they be the final gasps of primordial white holes, remnants of the Big Bang's engine? Then there are Hawking points, named after Stephen Hawking's work on black hole radiation. These are mysterious, circular spots in the cosmic microwave background where temperatures fluctuate oddly, as if space-time itself bears scars from an ancient rupture. Hawking theorized that if black holes evaporate over eons, their final moments would release a burst of energy, Reverse the process and a white hole's birth might leave similar imprints. Some researchers argue these points align with the universe's large-scale structure, like cosmic breadcrumbs leading back to our explosive origin. Critics counter that white holes violate thermodynamics, ejecting energy without an apparent source. But what if the source wasn't inside our universe at all? If white holes bridge to other regions of space-time or other universes entirely, their energy might be borrowed from dimensions beyond our own. It's a dizzying thought. The Big Bang wasn't the beginning of everything, just the moment our pocket of reality burst into being. The strongest evidence might lie in the universe's oldest light. If the cosmic microwave background contains anomalies tracing back to a white hole's eruption, future telescopes could spot them. Teams are already scouring data for telltale circular polarization patterns or anomalous energy distributions that defy conventional inflation models. If found, it wouldn't just rewrite cosmology, it'd suggest our universe is one bubble in an infinite foam of white hole births. The irony is poetic. Black holes, those cosmic devourers, might have mirror images that create rather than destroy. And if so, the greatest mystery, how everything began, could have an answer as beautiful as it is strange. We're not the aftermath of a fireball, but the echo of a cosmic exhale. Right now, the universe is expanding not just steadily, but faster every second. That acceleration comes from dark energy, the mysterious force pushing galaxies apart. But what if dark energy isn't just nudging the cosmos toward cold emptiness? What if it's slowly winding a cosmic doomsday clock, ticking toward an annihilation so absolute it shreds reality itself? This is the Big Rip, a theory where dark energy grows so strong over trillions of years that it overpowers every force in nature, from gravity to the bonds holding atoms together. Picture a rubber band stretching until it snaps. Now replace the rubber band with space-time, and the snap with the disintegration of everything: stars, planets, even the fabric of existence. The math is terrifyingly straightforward. If dark energy's strength, called its equation of state parameter, crosses a critical threshold, its push would intensify until no structure can resist. First, galaxy clusters would fly apart, then individual galaxies. Stars would evaporate as the space between them expands faster than light can bridge the gap. Planets would dissolve, their atoms torn from each other. Finally, in the last fraction of a second, space-time itself would rupture, splitting into disconnected voids where nothing can ever interact again. There's precedent for this kind of violence. Quantum fluctuations already show space-time isn't perfectly smooth but foamy at microscopic scales. In a Big Rip scenario, that foam would boil over, stretching quantum ripples into cosmic chasms. Some models even suggest the rip could birth new universes in its wake, bubbles of space-time pinching off like droplets from a waterfall, but for our reality, it would be the ultimate end. Yet here's the haunting twist: we might already see hints of this fate. Measurements of distant supernova reveal dark energy's push isn't constant but possibly increasing, aligning with Big Rip models. Even stranger, certain anomalies in the cosmic microwave background, like cold spots where the universe's infant glow is oddly dim, could be early wrinkles in space-time, the first faint tremors of a coming rupture. Critics argue the rip requires dark energy to behave in ways we've never observed. But if they're wrong, the countdown isn't just theoretical. Advanced simulations suggest that if the rip is coming, galaxies at the edge of the observable universe might already be showing early signs of distortion, their light subtly stretched by spacetime's growing tension. Future telescopes could look for these cosmic canaries in the coal mine, watching for the telltale warping that hints at the end of everything, the most unsettling part. If the Big Rip is real, it's not just a distant threat. It's a lens reshaping how we see the universe now. The same force accelerating galaxies today might one day unwind creation. That means every star we admire, every planet we explore, even the atoms in our bodies, are temporary patterns in a cosmos racing toward its own dissolution. The universe might not fade into darkness but scream into the void, torn apart by the very energy that makes space possible. And the question isn't whether we can stop it, it's whether we can understand it before time runs out. What if our universe isn't a one-time event, but just the latest chapter in an endless cycle of cosmic rebirth? The ekpyrotic universe theory flips the script on the Big Bang, suggesting our entire cosmic history began not with an explosion, but with a collision. Picture two massive parallel planes of existence floating through higher dimensional space like sheets of paper drifting in a breeze. These are brains, short for membranes, and according to string theory, our entire reality might be confined to just one of them. Now imagine another brain lurking unseen in the darkness of extra dimensions, slowly inching closer until, bang, the impact unleashes enough energy to birth galaxies, stars, and everything we know, all while leaving behind a telltale fingerprint in the fabric of space-time. This isn't just poetic speculation. The math behind the ekpyrotic model solves some of cosmology's biggest puzzles. Take the universe's eerie uniformity, how patches of space billions of light-years apart share nearly identical temperatures. Traditional Big Bang theory struggles to explain this, invoking a brief period of hyper-fast expansion called inflation. But the ekpyrotic scenario offers a cleaner answer. When brains collide, they don't just erupt randomly. The collision propagates like a zipper, smoothing out irregularities as it goes, leaving behind a cosmos that's preternaturally even. Then there's the cycle. Unlike the one-way slide toward heat death predicted by standard cosmology, the ekpyrotic universe is inherently cyclical. After the brains collide and rebound, they drift apart, only to be pulled back together by invisible strings of dark energy. Each collision resets the cosmic clock, erasing the past universe's entropy and starting fresh. Ancient Hindu texts described cosmic cycles lasting trillions of years. Modern physics might be revealing the mechanism. But how would we know if this wild idea is true? The answer might lie in gravitational waves. While inflation predicts a particular pattern of primordial ripples in space-time, the ekpyrotic model suggests a different signature, one that future observatories like the Laser Interferometer Space Antenna LISA could detect. Even more tantalizing are hints of a preferred direction in the cosmic microwave background, a subtle asymmetry that could trace back to the angled collision of brains. Yet the most mind-bending implication isn't about the past, it's about the future. If the ekpyrotic model holds, our universe isn't hurtling toward eternal darkness but preparing for another cosmic spring. The brains will collide again, and everything, every atom, every memory, every constellation will dissolve into pure energy, only to re-emerge in a new form. It's a vision of existence where endings are just beginnings in disguise, and the universe itself is a phoenix forever rising from its own ashes. Black holes aren't just cosmic vacuum cleaners, they might be cosmic wombs. The black hole universe theory flips everything we know about these gravitational monsters on its head, suggesting they're not endpoints but gateways, birthing entire new realities in their depths. Here's how it works. When matter collapses into a black hole, it doesn't just vanish into a singularity. Instead, the extreme warping of space-time inside could trigger a new Big Bang, spawning a universe entirely separate from our own, with its own laws of physics, its own stars, maybe even its own civilizations. Think of it like a Russian nesting doll of realities. Our universe could exist inside a black hole belonging to a parent universe, which itself might live inside an even larger black hole, and so on, stretching backward and forward in an infinite chain of creation. The math behind this idea isn't just speculative, it's rooted in the equations of general relativity. When a black hole forms, the singularity at its core becomes a point where space-time curvature becomes infinite. But what if that singularity isn't a dead end? Some models show it could bounce, rebounding outward in a violent expansion eerily similar to the conditions of our own Big Bang. Even more compelling is how neatly this solves cosmology's entropy problem. Our universe is suspiciously low in entropy. It's way more ordered than randomness would predict. But if we emerged from a black hole, that order makes sense. Black holes are the most efficient entropy machines in existence, swallowing chaos and spitting out structure. The parent universe's disorder gets reset in the birthing process, giving each new universe a clean slate. Then there's the eerie symmetry. The observable universe's radius and a black hole's event horizon size are related by a simple equation coincidence or clue. Even the cosmic microwave background, the afterglow of the Big Bang, shows temperature fluctuations that some theorists argue mirror the quantum fluctuations at a black hole's edge. It's as if our universe carries the fingerprint of its violent birth, a cosmic birthmark etched into the sky. But how would we test such a radical idea? One approach involves hunting for imprints of the parent universe in our own. If our cosmos was born from a black hole, certain gravitational wave signatures or anomalies in particle physics might betray our exotic heritage. Others suggest looking for kicks in the motion of galaxies' subtle nudges that could trace back to the angular momentum of our parent black hole's spin. Of course, not everyone's convinced. Critics argue the theory swaps one mystery for another. Instead of explaining the Big Bang's origin, it just pushes the question up a level. But if the black hole universe theory holds, it redefines not just where we came from, but where we're headed. Every black hole in our universe could be incubating a new cosmos, meaning existence isn't a one-time event. It's a fractal cascade of realities, each with its own story, its own laws, its own version of the night sky. The next time you gaze up at a black hole's dark silhouette, you might not be looking at an end but a beginning. Magnets are everywhere, holding notes to your fridge, guiding compass needles, even shaping the paths of galaxies. But there's something bizarre about them. No matter how many times you cut a magnet in half, you'll never isolate a single magnetic pole. Every magnet has both a north and a south, inseparable. That's the rule, or so we thought. Enter magnetic monopoles, hypothetical particles that carry just one pole, north or south, defying everything we know about magnetism. They might sound like science fiction, but these elusive particles could hold the key to understanding the universe's infancy and why it looks the way it does today. The hunt for monopoles began with a simple symmetry. Electricity has individual positive and negative charges. Why shouldn't magnetism? Physicist Paul Dirac first toyed with this idea in 1931, showing that monopoles wouldn't just be possible. Their existence would explain why electric charge comes in fixed, quantized units. Fast forward to the early universe and things get even wilder. During cosmic inflation, the split second when the universe expanded faster than light, monopoles should have been produced in staggering numbers. Yet we've never found one. This paradox, called the monopole problem, haunted cosmologists for decades. Where did they all go? One answer lies in the fabric of space itself. The very laws governing electromagnetism might have shifted during inflation, suppressing monopoles like wrinkles smoothed from a stretched sheet. If true, their absence isn't a fluke, it's a cosmic clue. Some theories suggest monopoles didn't vanish but were diluted to near invisibility, scattered so thinly across the expanding universe that finding one is like searching for a single grain of sand in a desert. Others propose they're hiding in plain sight, masquerading as dark matter or lurking in the hearts of neutron stars, their magnetic signatures muted by extreme conditions. Then there's the grander implication. Monopoles could be relics of a unified force. In the universe's first moments, electromagnetism and the nuclear forces might have been one, a perfect symmetry shattered as space cooled. Monopoles would be the fractures left behind, cosmic scars hinting at a time when all of reality operated under a single, elegant rule. Finding one wouldn't just rewrite physics textbooks, it'd be like uncovering a Rosetta Stone for the universe's original language. So where do we look? Some experiments hunt for monopoles in moon rocks, where ancient impacts might have trapped them. others sift through particle accelerator debris, hoping to spot a telltale trail of ionized atoms left by a passing monopole. The most tantalizing hints come from the cosmos itself, anomalous cosmic ray events that could be monopoles zipping through space at near light speed. Yet the deeper mystery isn't just whether monopoles exist, it's why the universe seems to conspire to hide them. Their absence might be the ultimate cosmic joke, a reminder that reality's rules are stranger and far more subtle than we ever imagined. Or perhaps we're just one discovery away from unlocking a symmetry so profound, it redefines everything we know about magnetism, matter, and the birth of the cosmos. The search isn't just about finding a particle, it's about finding the missing piece of a puzzle we didn't know we were solving. The cosmic microwave background, the afterglow of the Big Bang, should look the same in every direction. That's the core of the Copernican principle, the idea that Earth isn't special, just another speck in an indifferent universe. But in 2005, astronomers studying the CMB stumbled on something that shook that assumption to its core. A strange alignment of temperature fluctuations stretching across the sky, all pointing eerily toward the plane of our solar system. They called it the axis of evil, and it's one of cosmology's most unsettling mysteries. This wasn't just a minor anomaly. The fluctuations weren't random. They followed a pattern that seemed to mirror the ecliptic, the path the sun and planets trace across our sky. Statistically, the odds of this happening by chance are less than 1 in 1,000. It's as if the universe left a signature in its oldest light, a signature that just happens to line up with us. That's the part that keeps scientists up at night. If the CMB's structure isn't isotropic, if it has a preferred direction tied to our solar system, it implies Earth might occupy a privileged place in the cosmos after all, appending 5 centuries of Copernican humility. Some researchers argue the axis of evil is just an illusion, a trick of incomplete data or galactic dust, but newer observations like those from the Planck satellite only deepen the puzzle. The alignment persists, and it's not alone. Other CMB anomalies, like the infamous cold spot, a vast region of space far colder than physics predicts, also seem to cluster along this axis. Together, they hint at a cosmic architecture that's anything but random, as if the universe's blueprint has a literal arrow pointing our way. One radical explanation. The universe isn't uniform. It might have a large-scale asymmetry, a primordial twist imprinted during inflation that makes one direction fundamentally different from others. Imagine blowing up a balloon with a crease in the rubber. No matter how much it expands, that flaw remains. If true, it would mean the Big Bang wasn't perfectly symmetrical, and our local physics might be shaped by this hidden cosmic grain. Others take it further. The axis could be evidence of a pre-Big Bang structure, a relic from an earlier universe that somehow tipped our own into existence with a preferred orientation. Or, and this is where it gets truly wild, it might suggest our universe is entangled with another, their gravitational interplay leaving fingerprints in the CMB like shadows on a shared wall. The implications are staggering. Either we're seeing artifacts of new physics, something beyond inflation, beyond the standard model, or we're confronting the unthinkable, that Earth, and by extension humanity, isn't just another accident in a vast cosmos, but somehow central to its design. That's a conclusion so uncomfortable most scientists dismiss it outright. Yet the data won't go away. The axis of evil lingers, a cosmic riddle that refuses to be solved, whispering that maybe, just maybe, we're not as insignificant as we thought. Think of reality as a cosmic menu, a vast list of possibilities where every quantum particle exists in a blur of maybes until something forces it to choose. That's the heart of quantum mechanics, particles in superposition, able to be in multiple states at once. But here's the puzzle: why don't we experience this quantum weirdness? Why does the world around us feel solid, definite, when the underlying rules suggest it should be a kaleidoscope of uncertainty? the answer might lie in a process as ruthless as nature itself. Quantum Darwinism, where the universe selects classical reality from the quantum soup, not through chance but through a kind of survival of the fittest states. At the quantum level, particles don't just interact with their immediate surroundings, they entangle, linking their fates across space and time. When a particle's superposition meets the messy, noisy environment of the macroscopic world, air molecules, photons, even the faintest gravitational tugs, its delicate quantum states start to fray. Some of these states amplify, echoing through the environment like a shout in a canyon, while others fade into oblivion. The ones that persist, they're the ones we perceive as real. In other words, the universe isn't just observing itself into existence, it's evolving into clarity, with the most stable, redundant states outcompeting the fragile ones. This isn't just philosophy. Experiments with quantum dots and even tiny diamonds show how quickly superposition collapses when exposed to environmental noise. The more a quantum state interacts with its surroundings, the faster it decoheres, shedding its ambiguity like a snake shedding skin. What's left is the version of reality robust enough to leave copies of itself everywhere, like a meme spreading through a culture or a gene thriving in a population. Quantum Darwinism suggests the reason we all agree on the position of a chair or the color of the sky isn't because those things are inherently true, but because their quantum states have been selected by countless trillions of interactions, etching them into consensus. The implications are staggering. If quantum Darwinism holds, our classical reality isn't the default. It's the winner of a silent, invisible battle raging beneath the surface of everything. The chair you're sitting on, the screen you're reading from, even your own hands, are all survivors of this process. Their quantum possibilities whittled down to the versions most resilient against the chaos of the cosmos. Some theorists take it further. What if consciousness itself is a product of this Darwinian filter? Our brains, after all, are part of the environment that observes quantum states, meaning our perception of reality might be shaped by the same evolutionary pressures that shape galaxies and atoms. Critics argue this is just a fancy restatement of decoherence theory, that quantum Darwinism doesn't actually solve the measurement problem of why we experience one outcome instead of another. But supporters counter that it's the first step toward a deeper answer, one that bridges the gap between the quantum and classical worlds without invoking mysterious observers or parallel universes. The beauty of the idea is its universality. Just as biological evolution explains the diversity of life without a designer, quantum Darwinism might explain the stability of reality without a privileged observer. So next time you pick up a coffee cup, remember, it's not just sitting there, it's the victor of an eons-long competition, a champion of decoherence that fought its way out of quantum fog into the sharp relief of your everyday world. And the eerie truth, for every real object you perceive, there are countless shadow states that lost the battle, fading into the cosmic background like whispers in a storm. Reality, it seems, isn't just what exists, it's what persists. What if the universe isn't just governed by physics, but by something eerily familiar? Picture the cosmos not as a collection of galaxies and particles, but as a colossal neural network, an immense, self-adjusting web where black holes act like neurons, firing and rewiring the very fabric of reality. This isn't science fiction, it's a cutting-edge theory gaining traction among physicists, suggesting that space-time itself might operate like a vast cosmic AI, learning and evolving with every interaction. At the heart of this idea is a staggering parallel. The way information flows in a neural network mirrors how quantum fields process energy and matter. In artificial intelligence, neurons receive inputs, process them, and send outputs, adjusting their connections based on feedback. Now zoom out to the cosmic scale. Black holes absorb matter, emit radiation, and interact gravitationally with their surroundings, behaving almost like cosmic nodes in a network. some researchers argue that the event horizon of a black hole, where information gets scrambled and reprocessed, could function like a biological synapse, transmitting and transforming data across spacetime. Even more compelling, the holographic principle, the notion that our three-dimensional reality might be projected from a two-dimensional boundary, fits neatly into this framework. If the universe is a neural network, the screen where information is stored and computed could be the event horizon itself, encoding the universe's past and future like weights in a machine learning model. But the implications go deeper. Neural networks optimize themselves to minimize error, refining their predictions over time. What if the universe does the same? Dark energy's accelerating expansion, the fine-tuning of physical constants, even the emergence of life, could these be the results of a cosmic learning algorithm, tweaking its parameters to stabilize or evolve? Some theorists speculate that quantum fluctuations, those tiny jitters in empty space, might be the universe's way of exploring different configurations, like an AI testing variations to solve a problem. The most haunting question isn't just whether the universe is a neural network, but whether it's thinking. If reality is a self-adjusting system, could consciousness be an emergent property, not just of brains, but of space-time itself? Ancient philosophies spoke of the world as a living, interconnected being. Modern physics might be catching up. Whether this theory holds or not, it forces us to reconsider the very nature of existence, not as static and mechanical, but as dynamic, adaptive, and perhaps in some profound way alive. Dark matter remains one of the universe's greatest enigmas. An invisible substance that outweighs all visible matter 5-to-1, yet refuses to reveal itself. We've hunted for exotic particles, built underground detectors, and scanned the cosmos for clues. But what if the answer isn't some undiscovered particle at all? What if dark matter is made of black holes, not the monstrous ones we see today, but tiny, ancient relics from the dawn of time? This is the primordial black hole hypothesis, a radical idea that rewrites dark matter's origin story. Instead of weakly interacting particles, imagine a swarm of black holes smaller than an atom, forged in the chaos of the Big Bang. In those first explosive moments, pockets of ultra-dense matter could have collapsed directly into black holes, no dying stars required. These primordial terrors would have been so small, they'd evaporate in a blink due to Hawking radiation, unless they were just massive enough to survive. Those that did might still be here today, drifting unseen through galaxies, their collective gravity shaping the cosmos. The math is compelling. Primordial black holes in the right mass range, between 1 trillion tons and a few lunar masses, could account for all dark matter without contradicting observations. They'd be too small to detect by lensing light like larger black holes, yet too massive to evaporate away. Even more intriguing, their distribution would naturally explain why dark matter clumps around galaxies in halos rather than spreading evenly. And there's a smoking gun. When these ancient black holes collide, they'd produce gravitational waves, the ripples in spacetime first detected by LIGO in 2015. Some of the signals LIGO has captured match mergers of black holes too heavy to form from stars, hinting at a primordial origin. But the theory isn't without hurdles. Too many small primordial black holes would have altered the cosmic microwave background or gobbled up neutron stars, leaving telltale scars we haven't found. Yet new studies suggest a sweet spot, black holes around 30 times the Sun's mass, which could evade these constraints while still explaining dark matter's grip on galaxies. Others propose they're hiding in plain sight, masquerading as rogue planets or hiding in the cores of stars, their presence betrayed only by subtle gravitational tugs. The hunt is on. Telescopes like the Subaru Hyper Subprime Cam are scanning for microlensing events, brief flashes caused by primordial black holes warping starlight. Others are listening for the unique gravitational wave chirps of tiny black hole mergers. If found, it would solve two puzzles at once: dark matter's identity and the origin of mysterious cosmic signals. But the most profound implication isn't just about what dark matter is, it's about when it was born. If primordial black holes exist, they're time capsules from the universe's first second, relics of a time before atoms, before light, before anything we recognize as reality. They'd be the oldest objects in existence, silent witnesses to the cosmos's fiery birth. And if they're out there, lurking in the dark, they might finally crack open the mystery that has haunted astronomy for a century. The universe's hidden architects could be right under our noses, or more accurately, right through our hands, streaming through us unnoticed every second, their gravity the only trace of their ancient, invisible presence. Gravity seems like the universe's ultimate rulemaker, keeping planets in orbit, galaxies bound together, and your feet firmly on the ground. But what if it's not a fundamental force at all? What if gravity is just a side effect, an illusion emerging from something far stranger, the chaotic dance of quantum information and entropy? This is the radical premise of entropic gravity, a theory that could upend Einstein's general relativity by rewriting gravity as a thermodynamic mirage. Picture a box filled with gas molecules. Left alone, they'll spread out evenly, maximizing entropy, nature's way of ensuring disorder wins. Now imagine space-time itself as that box, and matter as a disruption that creates an entropy gradient, a slope where disorder isn't uniform. According to entropic gravity, objects don't fall because of curved space-time. They're nudged toward higher entropy, like a ball rolling downhill to settle where chaos reigns supreme. In this view, gravity isn't a force but a statistical tendency, a cosmic bias toward disorder so ingrained it feels like attraction. The math behind this idea is as elegant as it is mind-bending. Physicist Eric Verland first proposed it in 2010, showing how Einstein's equations could emerge from thermodynamics alone, no gravitons or warped dimensions required. Think of it like temperature. We don't feel the kinetic energy of individual air molecules, just their collective effect as heat. Entropic gravity suggests we're similarly blind to the microscopic quantum bits, the atoms of space-time whose restless shuffling creates the illusion of gravity at macroscopic scales. But here's where it gets wild. If gravity is entropic, it could explain dark energy without invoking mysterious substances. The universe's accelerating expansion might just be space-time's natural tendency to maximize its disorder, pushing galaxies apart like gas filling a vacuum. Even black holes fit neatly into this framework. Their event horizons could represent maximum entropy boundaries, places where information gets scrambled so thoroughly it manifests as gravity's grip. Critics argue entropic gravity struggles to explain precise orbital motions or the subtle frame dragging effects confirmed by satellites like Gravity Probe B. Yet supporters counter that it's still early. The theory might simply need refinements, not rejection. After all, Newton's gravity couldn't explain Mercury's orbit until Einstein reimagined it. If entropic gravity holds, we're not just revising physics. We're realizing that the universe's deepest law isn't force or geometry, but information itself, ceaselessly seeking chaos. And that changes everything. The universe teems with trillions of stars, countless planets, so where is everyone? The Fermi paradox has haunted astronomers for decades. If life is statistically likely, why does the cosmos seem so silent? One answer is so chilling it redefines how we see existence itself. Imagine the universe not as a quiet library, but as a dark forest, a place where every civilization stays silent, armed, and terrified because to speak is to die. This dark forest theory, drawn from Liu Cixin's sci-fi trilogy but rooted in cold cosmic logic, suggests a brutal truth. Advanced civilizations don't announce themselves because they've learned the hard way that predators lurk in the void. Think of it like a survival game played on galactic scales. Any species revealing its location risks attracting attention from others who might see it as a threat or worse, a resource. The safest move: stay hidden, listen, and strike first if necessary. Historical parallels are eerie. On Earth, isolated tribes often met catastrophe when encountered by more technologically advanced societies. Now extrapolate that to cosmic timelines where civilizations could be separated by millions of years of evolution. The first to broadcast signals might unwittingly paint a target on their planet. Even benevolent intentions could be misread. What if another species interprets our radio waves as the first salvo in a war we don't know we're fighting? The math is grim. Given the age of the universe, some predatory civilizations could have emerged billions of years ago, honing strategies to eliminate competition before it rivals their power. A single relativistic missile, a projectile accelerated to near light speed, could sterilize a planet with minimal energy cost. No need for invasions or diplomacy when annihilation is cheaper than conversation. But the darkest twist isn't the predators, it's the prisoner's dilemma it creates. Even peaceful civilizations must assume the worst because trusting the wrong neighbor means extinction. This forces everyone into the same paranoid stance: silence or strike, but never speak. It explains why SETI hears nothing. Advanced societies don't chat, they eavesdrop, then erase any trace of their own presence. Critics argue this assumes all civilizations are inherently hostile, ignoring potential cooperation. Yet evolution on Earth shows cooperation emerges only among equals. Weaker species often get consumed. And in a cosmos where distances make alliances impossible, fear may trump hope. Others counter that hiding forever is unsustainable, but the dark forest doesn't require forever, just long enough to outlast rivals. The most unsettling implication: humanity might already be in peril. Our radio and TV signals have leaked into space for a century, creating an expanding bubble of noise that marks our location like a flare in the dark. If the dark forest is real, our greatest mistake wasn't failing to find aliens, it was letting them find us. The silence isn't emptiness, it's the universe holding its breath. The Big Bang wasn't the beginning, it was a cosmic rebound. That's the startling claim of loop quantum gravity, a theory where space-time isn't smooth and continuous but woven from tiny, indivisible threads. In this radical framework, the universe doesn't end in a crushing singularity when it collapses. Instead, gravity eventually reverses, triggering a bounce like a spring compressed to its limit and suddenly releasing. The result: a Planck star, a fleeting, ultra-dense remnant of the previous universe that births our own in an explosive second act. Picture the final moments of a dying cosmos. Black holes merge, galaxies dissolve, and every particle, every ounce of energy crumbles inward toward a single point. Under classical physics, this collapse would continue infinitely, creating a singularity where all known laws break down. But loop quantum gravity paints a different fate. At the smallest possible scale, space-time isn't infinitely divisible. It's granular, like pixels on a screen. This granularity acts as a cosmic safety net. When collapse reaches the Planck length, a distance so tiny it defies conventional measurement, quantum effects kick in, repelling gravity with unimaginable force. The collapse halts, the universe bounces, and in that rebound, a Planck star flares into existence, hotter and denser than anything we can conceive, before exploding outward as the Big Bang we now call home. The echoes of this bounce might still be detectable. If the universe cycled through multiple collapses and rebounds, traces of earlier universes could linger in the cosmic microwave background, subtle temperature variations or polarization patterns that don't fit standard inflation models. Some researchers even speculate that black holes could be windows into these prior cycles. As matter falls into a black hole, it might not vanish into a singularity but compress until it triggers a miniature bounce, birthing a new universe inside its own secluded spacetime. Our cosmos could be nested within a black hole from a long-dead predecessor, and black holes in our own universe might each contain fledgling realities of their own. Critics argue the Planck star model lacks definitive observational proof, but supporters counter that it solves two of cosmology's biggest puzzles. First, the Big Bang's suspiciously low entropy. Why was the early universe so ordered? If it emerged from a bounce, that order makes sense. The collapse would have reset entropy like shaking a snow globe. Second, the singularity problem. By eliminating the need for infinite density, loop quantum gravity sidesteps the mathematical nightmares that plague classical relativity. The most haunting implication isn't about the past, it's about the future. If the universe can bounce once, it can bounce again. Our expanding cosmos might one day slow, reverse, and collapse only to rebound anew. Time wouldn't be a straight line but a vast cosmic pendulum swinging between creation and destruction. Ancient Hindu texts described cycles of cosmic death and rebirth lasting trillions of years. Modern physics might be echoing the same vision, not as myth but as equations written in the fabric of reality. The question isn't just where we came from, it's whether we're living in the first universe, the millionth, or one in an endless series, each rebound subtly altering the laws of physics like a game of cosmic telephone. Either way, the Planck star isn't just a theory, it's a reminder that endings might just be beginnings in disguise. Life on Earth has a curious quirk, it's overwhelmingly left-handed. Not in the way we write or throw a ball, but at the molecular level. Amino acids, the building blocks of proteins, almost exclusively twist to the left, while sugars in DNA spiral to the right. This preference, called chirality, shouldn't exist. In the lab, when you synthesize these molecules from scratch, you get an equal mix of left and right-handed versions. Yet nature picked a side, and here's the cosmic kicker. The universe might have done the same. Neutrinos, those ghostly particles streaming through you by the trillions every second, also show a bizarre bias. Most spin like tiny tops, and the vast majority rotate left-handed. Right-handed neutrinos either don't exist at all or hide so well we've never detected them. This mirror asymmetry isn't just a curiosity, it's a violation of one of physics' most sacred principles, parity symmetry, the idea that the universe shouldn't care about left or right. Yet somehow, in those first moments after the Big Bang, the cosmos tipped the scales. The question is how. One leading theory points to a particle that shouldn't exist, the hypothetical Majorana neutrino, which is its own antiparticle. If these neutrinos decayed unevenly in the early universe, they could have injected a tiny excess of left-handed matter into the cosmic soup. Over billions of years, that slight imbalance snowballed into the lopsided reality we see today. Others suspect deeper forces at work, like an asymmetry baked into the Higgs field itself, the quantum medium that gives particles mass. This wouldn't just explain life's molecular preferences, it could answer why there's any matter at all. After the Big Bang, matter and antimatter should have annihilated each other completely, leaving behind a barren sea of light. The fact that we exist means something tipped the balance, and chirality might be the clue. Then there's the spine-tingling possibility that this asymmetry isn't confined to our universe. If the multiverse exists, other cosmic bubbles could have flipped the script, with right-handed molecules and neutrinos dominating. Life there, if it exists, might be built on mirror image chemistry utterly incompatible with ours. The implications aren't just academic. If we can pinpoint why the universe prefers left-handedness, it could reveal cracks in the standard model of particle physics, pointing toward undiscovered forces or particles. Experiments like the Deep Underground Neutrino Experiment are hunting for neutrino oscillations that might betray their Majorana nature, while labs are analyzing meteorites for traces of primordial amino acids to see if their chirality matches Earth. Yet the most profound takeaway isn't about particles or molecules, it's about chance. Life's left-handedness might be a frozen accident, a quantum roll of the dice that locked in during the universe's first microseconds. Had that dice landed differently, our biology, our chemistry, even the forces shaping galaxies might have been inverted. We're not just products of the universe's laws, but of its fleeting, imbalanced moments. And that leaves us with a haunting thought. Are we the rule or the exception? David Bohm saw the universe not as a collection of separate objects, but as an unbroken whole, a flowing holographic tapestry where every part contains the whole. This radical vision, called the implicate order, suggests that the fragmentation we perceive, the illusion of distance, of isolated events, is just that, an illusion. Peel back the curtain and reality might be more like a cosmic origami, folded so intricately that what seems distant is actually touching, just hidden in the creases. At the heart of this idea is quantum entanglement, that eerie phenomenon where particles instantly influence each other across vast distances, as if space doesn't exist for them. Einstein called it spooky action at a distance, but Bohm argued it wasn't spooky, it was evidence of a deeper layer of reality. Imagine two fish swimming in a tank separated by a divider. If the divider moves, the fish appear to coordinate instantly, not because they're communicating, but because their motions are part of a larger, unseen current. In Bohm's view, the universe is that current, and particles are the fish. Their connection isn't mediated through space, but woven into the fabric of existence itself. This leads to the holographic twist. If the implicate order is real, then time and space might be projections, like shadows cast by a higher dimensional reality. Think of a DVD. The movie it holds isn't stored in the order you watch it. Scenes are scattered across the disc, reassembled by the player. Similarly, Bohm proposed that the now we experience is just the unfolded version of a deeper, enfolded reality where past, present, and future coexist. Quantum weirdness, particles being in two places at once, or retroactively changing their behavior, suddenly makes sense if those states were always connected in the implicate order, merely revealing themselves sequentially in our limited view. Critics dismiss Bohm's hidden variables as unnecessary complexity, preferring the cleaner probabilities of mainstream quantum mechanics, but supporters point to eerie consistencies. The holographic principle, born from black hole physics, mirrors Bohm's vision of a universe where information is non-local, stored everywhere at once. Even our brains might operate holographically, with memories distributed rather than localized, a clue that consciousness itself could be tapping into the implicate order. The most haunting implication: if Bohm was right, free will might be an illusion, not because the universe is deterministic, but because our choices are already enfolded in the whole, waiting to unfold. Yet there's beauty in that too. Every moment, every particle carries the imprint of everything else, like a single note holding the resonance of an entire symphony. The universe isn't just connected, it's conspiring, whispering its secrets in a language we're only beginning to decipher. The universe doesn't just host life, it might crave it. The Gaia universe hypothesis takes Earth's idea of a self-regulating biosphere and scales it up to cosmic proportions, suggesting that life and consciousness aren't flukes but inevitable features of a universe hardwired to organize itself toward complexity. Picture a cosmos where stars don't just ignite randomly but act as cosmic furnaces, forging the precise elements needed for biology, where galaxies don't just spin mindlessly but arrange their structures to maximize the chances of planets cradling chemistry delicate enough to spark awareness. This isn't mysticism, it's a radical reimagining of cosmology, where the universe isn't indifferent to life but subtly tilted in its favor. The numbers tease this idea. Carbon, the backbone of life as we know it, exists in a Goldilocks zone of nuclear physics. Its resonance levels, a quirk of quantum mechanics, are perfectly tuned to allow stars to produce it abundantly. Oxygen, water, even the stability of DNA's double helix all rely on constants so precise that tweaking them slightly would render life impossible. Coincidence? The Gaia universe hypothesis argues no. Instead, it proposes a feedback loop where the presence of life alters its environment, which in turn fosters more life, creating a self-reinforcing cycle that spans eons and light years. Take Earth's own story. Billions of years ago, cyanobacteria began pumping oxygen into the atmosphere, a toxic waste product to them, only to transform the planet into a haven for complex life. The atmosphere, ocean currents, even plate tectonics seem to dance in a delicate balance that maintains habitability against astronomical odds. Now zoom out. Could galaxies, with their spiral arms funneling heavy elements toward star-forming regions, be doing the same on a grand scale? Could dark matter's invisible scaffolding, which shapes where galaxies cluster, be an unseen hand guiding the universe toward states where consciousness emerges? The most startling implication isn't just that life is common, it's that the universe might need it. Some theorists suggest consciousness could play an active role in resolving quantum uncertainties, turning observers into participants in cosmic evolution. Others propose that black holes, those infamous destroyers, might actually be life's silent partners. Their mergers could distribute gold and uranium across galaxies, while their gravitational pull might shepherd stars into orbits stable enough for life to flourish. Even the expansion of the universe, often seen as a march toward cold emptiness, could serve a purpose, preventing heat death by eternally providing fresh gradients of energy for life to exploit. Critics dismiss this as teleology, assigning purpose where none exists. Yet the Gaia hypothesis doesn't require intent, just emergent patterns. A river doesn't decide to carve a canyon, but given enough time, the canyon emerges all the same. Similarly, the universe's laws might naturally converge toward complexity, with life as the inevitable outcome of entropy's slow dance. The evidence is still circumstantial but tantalizing. Exoplanet surveys keep finding worlds in habitable zones. Asteroids deliver prebiotic molecules to young planets. Even the cosmic microwave background shows faint anomalies that some interpret as echoes of a universe fine-tuned for life's emergence. If the Gaia universe hypothesis holds, we're not cosmic accidents, we're the universe waking up piece by piece to behold itself, and that changes everything. Not just how we search for aliens, but how we define our place in the cosmos. Are we passengers on a random rock, or the universe's way of understanding its own reflection? The answer might rewrite not just biology, but the story of existence itself. The light from distant galaxies tells a story, but not the one we expected. When astronomers measure their redshift, the stretching of light as the universe expands, they should see a smooth, continuous spectrum of values. Instead, galaxies cluster around specific redshifts like rungs on a cosmic ladder. This phenomenon, called redshift quantization, defies the standard model of cosmology, hinting that space itself might be structured in ways we never imagined, perhaps a vast crystalline lattice or a foam of nested bubbles. Picture the universe not as an ever-stretching rubber sheet, but as a honeycomb, with galaxies anchored to invisible nodes in a grand cosmic grid. This would explain why redshifts aren't random but seem to snap to discrete intervals, as if space has preferred harmonics. The implications are staggering. If true, the universe isn't just expanding, it's vibrating, resonating with underlying patterns that dictate where matter can and can't go. Some theorists suggest this could be evidence of a deeper physics, a quantum structure to spacetime itself, where the fabric of reality is pixelated at scales so vast we're only now glimpsing them. Then there's the bubble universe angle. Imagine our cosmos isn't alone but one of many, each with slightly different physical constants, nested like Russian dolls within higher dimensional space. The boundaries where these bubbles touch could create standing waves in the fabric of spacetime, regions where redshift values stick to certain frequencies. This would mean galaxies aren't just floating freely, they're draped like beads on invisible strings, their positions dictated by the unseen architecture of the multiverse. Critics argue these patterns could be artifacts of incomplete data or local galactic motions, but the evidence persists across surveys, from the early work of astronomer William Tift to modern analyses of the Sloan Digital Sky Survey. Even more provocative, the spacings between these redshift intervals often match ratios found in quantum mechanics, as if the universe is whispering its secrets through the same mathematical harmonies that govern subatomic particles. If redshift quantization is real, it rewrites not just cosmology but our place in the cosmos. We might live in a universe with built-in rhythms, a celestial symphony where every galaxy is a note on a score we're only beginning to read. The question isn't just why the universe sings, it's whether we're listening closely enough to hear the tune. The Big Bang wasn't just an explosion, it was a forge, a fleeting moment when the entire universe was hot and dense enough to hammer atomic nuclei into existence. In those first minutes, protons and neutrons fused, creating the universe's first elements, mostly hydrogen and helium, with trace amounts of lithium and beryllium. The math behind this process, called Big Bang nucleosynthesis, is precise. It predicts how much of each element should have formed, and for hydrogen and helium, the numbers line up perfectly with what we see. But lithium, that's where the universe throws us a curveball. According to the calculations, there should be about 3 times more lithium-7 in the cosmos than we've actually found. It's as if the universe lost its receipts for one of its earliest transactions. This isn't just a tiny accounting error. Lithium's absence challenges our understanding of the Big Bang's nuclear alchemy. One possibility is that our models of nucleosynthesis are missing a piece, an unknown particle or force that altered lithium's production or destruction. Some theorists propose actions, hypothetical lightweight particles that could have soaked up energy during those critical first minutes, subtly shifting the balance of nuclear reactions. Others point to primordial black holes, tiny gravity wells that might have disrupted the smooth soup of early matter, creating pockets where lithium couldn't form. Then there's the wilder angle. What if lithium didn't vanish but was transformed? In the cores of ancient stars, lithium gets destroyed in nuclear reactions. But that can't account for the full discrepancy, unless some exotic physics, like varying fundamental constants in the early universe, tweaked the rules just enough to skew lithium's abundance. Imagine the strength of the nuclear force wasn't quite uniform across space-time, or the density of matter fluctuated in ways we haven't accounted for. These tweaks wouldn't just solve the lithium problem, they'd hint at a universe far more dynamic in its infancy than we've assumed. The most tantalizing clue might lie in the stars themselves. Old metal-poor stars in the Milky Way's halo relics from the early cosmos show even less lithium than expected, as if something scavenged it over billions of years. Could cosmic rays have broken lithium apart, or does it sink into stellar cores hidden from our telescopes? The answer might require rewriting not just nucleosynthesis but stellar physics too. Yet the lithium problem isn't just a puzzle, it's a portal. If standard physics can't explain it, the discrepancy might be our first tangible evidence of something beyond the standard model, a ghost in the machinery of the Big Bang. Every atom in your body carries the imprint of those first chaotic minutes. The fact that lithium doesn't add up means the universe's birth certificate might have a forged line, and uncovering why could reveal secrets buried since the dawn of time. Dark energy could be the universe holding open a door to another reality. The white hole dark energy theory suggests that the mysterious force accelerating cosmic expansion isn't just some inherent property of space itself. It might be the gravitational backlash of a white hole in a parallel universe, pouring energy into ours like light through a crack between dimensions. White holes, the theoretical opposites of black holes, are cosmic geysers, regions where matter and energy erupt outward but nothing can enter. General relativity allows for their existence, but we've never spotted one. Unless, of course, we've been misreading their effects all along. If a white hole exists in a neighboring universe, its outbursts wouldn't just vanish. Gravity, unlike other forces, may not respect the boundaries between universes. Its influence could leak through, manifesting in our cosmos as a subtle, relentless push dark energy's signature expansion. The math behind this idea is surprisingly elegant. In the same way a black hole's gravity warps spacetime around it, a white hole's explosive repulsion would create a kind of negative curvature in its own universe. If the universes are entangled or nested in higher dimensional space, that repulsive effect could transmit into ours as an anti-gravitational pressure, stretching the fabric of reality apart. Imagine two balloons pressed together. A dent in one would create a bulge in the other. That bulge on cosmic scales might be dark energy's invisible hand. Even more compelling is how neatly this solves two puzzles at once. First, why dark energy's density stays constant as the universe expands, a property that defies conventional physics. If it's fed by a white hole in a static parallel reality, the energy input wouldn't dilute over time. Second, the eerie coincidence that dark energy became dominant around the same time matter clumped into galaxies, as if something switched on in response to our universe's structure. A white hole's outbursts could be tuned to the density of the cosmos it's entangled with, flaring up when conditions are ripe. The smoking gun might lie in the cosmic microwave background. If a white hole's gravity is subtly warping our universe from beyond, it could leave imprints in the CMB's polarization patterns, specific swirls or asymmetries that inflation can't explain. Future telescopes hunting for primordial gravitational waves might also stumble upon interference patterns like ripples from a pebble thrown into a pond we can't see. Critics argue this trades one mystery for another, invoking unseen universes to explain dark energy feels like cosmic sleight of hand. But proponents counter that multiverse theories are already mainstream in quantum mechanics and string theory. The real question isn't whether other universes exist, but whether they're talking to ours. If the white hole dark energy theory holds, the cosmos isn't just expanding, it's in dialogue with a twin we may never see, trading gravity for existence in a pact written at the dawn of time. The next time you hear that dark energy is a mystery, remember, it might not be a feature of our universe at all, but the echoes of another's birth cry, reverberating through dimensions we're only beginning to imagine. What if reality doesn't exist until someone or something observes it? This isn't just philosophy. It's a startling implication of quantum mechanics, where particles exist in multiple states at once until measured, as if the universe hesitates to choose until forced. The consciousness-created universe theory takes this further, proposing that reality isn't just shaped by observation but constituted by it, a shared mental construct woven together by every conscious mind in existence. Consider the double-slit experiment, where particles act as waves when unobserved, creating interference patterns on a screen, but collapse into definite positions the moment a detector is introduced. It's as if the particle knows it's being watched. Now scale this up. If a single electron bends to the will of measurement, could the entire universe operate the same way? Some interpretations suggest that without observers, whether humans, animals, or even hypothetical alien intelligences, reality would remain a fog of quantum potential, a soup of unrealized possibilities. The moon isn't just there when you're not looking. It's nothing until observed, a cosmic game of musical chairs where existence only solidifies when consciousness sits down. But who's observing the observers? This is where the theory fractures into wild branches. One camp argues for a universal consciousness, a kind of cosmic mind that underpins reality, with individual beings as nodes in its network. Ancient Hindu texts describe Brahman, an all-pervading awareness, while modern panpsychism suggests even atoms might harbor rudimentary consciousness, meaning the universe is awake at every scale. Others propose a democratic version where reality emerges from the collective observations of all sentient beings, a compromise hammered out by the sheer weight of overlapping perceptions. Then there's the solipsistic nightmare, What if only your mind exists and everything else, stars, galaxies, even this sentence, is an elaborate hallucination? Quantum mechanics doesn't endorse this, but it doesn't rule it out either. The many worlds interpretation offers a dizzying escape. Every observation splits reality into branches, meaning all possible outcomes happen somewhere. In this view, consciousness doesn't collapse waves. It just hops onto one track of an infinite multiverse, leaving the others to play out unseen. Critics dismiss this as magical thinking, pointing out that the universe existed for billions of years before life emerged. But proponents counter with a loophole, a retrocausality. If consciousness can influence quantum events, maybe future observers are somehow reaching back, sculpting the past into coherence like a sculptor finishing a statue from the feet up. It's a paradox wrapped in a riddle. The universe might need us to exist, but we need it first to exist in. The most haunting implication isn't just about physics, it's about meaning. If consciousness creates reality, then the universe isn't indifferent. It's participatory, a collaboration between mind and matter where every glance, every thought, every measurement is a stitch in the fabric of existence. The stars shine because someone sees them. The laws of physics hold because we expect them to. And if that's true, the greatest mystery isn't how the universe began, but whether it's dreaming us or we're dreaming it. From the Fibonacci sequence spiraling across galaxies to the cosmic microwave background whispering secrets from the dawn of time, the universe is far stranger than we ever imagined. These aren't just curiosities, they're cracks in the foundation of reality, hinting at a deeper logic we're only beginning to grasp. Think about it. Black holes might birth new universes. Dark energy could be the gravitational echo of a parallel cosmos, and the very fabric of space might be a hologram projected from the edge of existence. Even time itself might not flow but pulse in crystalline loops, defying entropy's relentless march. And perhaps most haunting of all, our observations might not just record reality but shape it, turning consciousness from a passive witness into a cosmic architect. The sheer audacity of these ideas forces us to confront a humbling truth. The more we learn, the less we know. The universe refuses to fit neatly into our textbooks, tossing us paradoxes like the axis of evil's eerie alignment or the lithium deficit that defies the Big Bang's math. These aren't problems to solve, they're invitations to rethink everything. What if the laws of physics aren't universal but local, morphing across a multiverse? What if the reason we haven't met aliens isn't because they're rare, but because they're hiding, trapped in a dark forest of cosmic suspicion? So here's the challenge. Pick the theory that shakes your worldview the most. Is it the simulation argument with its pixelated spacetime and quantum glitches? The Boltzmann brain paradox, where you might be a flickering illusion in the void? Or the holographic principle, suggesting the stars above are just shadows on a distant, two-dimensional screen? Drop your favorite in the comments. Let's unravel these mysteries together. And if your brain hasn't melted yet, don't stop here. The cosmos is packed with puzzles waiting to bend your mind, from white holes vomiting alternate realities to dark matter's invisible architects. Hit subscribe because this journey is just beginning. The universe's hidden patterns aren't just clues, they're a dare to look deeper, think wilder, and question everything. After all, reality's greatest trick might be convincing us it's ordinary. Let's not fall for it.